In this video, what we are going to discuss is the face-centered cubic structure. Let me start with today's video, that is about face-centered cubic structure, FCC. In short, we write it FCC structure. So FCC stands for face-centered cubic. Okay, so if we have the unit cell of this kind in a crystal, so this is a cubic crystal where the atoms are kept at the 8 corners as well as the centers of each and every face of this cube. So this is one face, this is another face, this is the side face, this is the upper face, and this one is the front face center, and the other one is the last front side. In totality, if we count, there are 8 atoms at the corners and 6 atoms at the center of 6 faces. But what is the effective contribution of these atoms to this single unit cell? This figure that we have shown here, this represents a single unit cell of FCC structure, single unit cell of FCC structure. So what we will count is, we will count the first of all effective number of atoms. Effective number of atoms in the unit cell. So as we discussed in case of simple cubic, there are 8 atoms at the 8 corners. So effective contribution of the corner atoms is precisely 1. So 8 atoms at the 8 corners, and 1 atom present at the corner is actually contributing 1/8 of its volume to the single cube, because this structure, this figure that we have drawn here, is repeated in 3 dimensions. So in 3 dimensions, if we see, I discussed it in quite detail in my previous video. So the effective contribution of the corner atoms, 8 corner atoms, is precisely 1, and plus the 6 face centered atoms which are present at the center of each and every face. And since each face, if we repeat this unit cell in all 3 dimensions like this, so we will see that each face centered atom is being shaded by 2 faces. Okay, these are the 2 cubes, number 1 cube and let's say number 2 cube. So this particular atom which I have shaded as dark is being shared by 2 faces of 2 different cubes, 1 and 2. So the effective contribution to the 1 unit cell is half. So if I count the total number, that comes out to be 4. Okay, so effective number of atoms, the unit cell of a FCC cubic FCC structure is 4. The second thing that we would like to find out is the relation between the radius of an atom. Suppose, let's say, the radius of an atom is, let's say, r, and the edge of the cube is, let's say, a. So if the edge is a, and we would like to find out the relation between r and a. So if we draw, suppose if I draw a picture of one single face of this cube, so what how does it look like? It looks like this. Okay, we suppose I have shaded this portion with green, this face with green, which I have drawn here. So there is 1 atom at the center of this face and 4 at the corners, but this is how we depict it. But in reality, the situation is something like this. So assuming all these 3 atoms to be identical, although they appear to be of different size because I have drawn them by my hand, but they are, in actuality, they are all three are of the same size. So same radius, same diameter. Okay, so let's say the radius to be r. So this is the complete diameter will become 2r here, and this r, and this also and this edge is a. The edge of the cube is a. So 4r basically is equal to root 2a. So 4r is equal to root 2a means that the r is actually equal to a by 2 root 2. right? So that's what we get as relation between R and A. The third thing we would like to find out is the number of nearest neighbors, and before that we can find out actually the distance from the nearest neighbor. So distance from the nearest neighbor. Okay, so what suppose I focus my attention to let me draw the cube first of all once again, and then I would explain the nearest neighbors, concept of nearest neighbors. Okay, so let me represent the atom with different color. 1 2 3 4 5 6 7 8 corners, and the center 1 2 3 4, and the front one and the back one. Okay, so if I let's say focus my attention to this particular atom which I have darkened, and would like to see that what are the atoms which are closest to this particular atom that I have just darkened. So if we focus our attention here, and we'll see that these distances that I have drawn here, they are precisely equal, and they are equal to a by root 2, right? Because the diagonal of the square will be root 2a, and the distance is half of the diagonal. So this is equal to, let me write this atom as O, let me write this as A. So OA is actually nothing but a by root 2, and there is no other atom which is closer to this particular atom which is marked as O, and situated at a distance which is less than a by 2. All right, so the nearest neighbors distance that turns out to be a by root 2. Okay, so nearest neighbor distance is nothing but a by root 2, which is actually root 2a by 2, which is a by root 2. Okay, and because in the figure itself, if we concentrate this on this O atom at the center, the closest atoms present in the vicinity are these four atoms that I have written here, 1 2 3 4. Okay, so now are these are these the only atoms that are situated at a by root 2 distance? Are there other atoms as well? It means we want to find out the total number of nearest neighbors. So the total number of nearest neighbors, total number of nearest neighbors, or you can call, if you wish, you can call out first nearest neighbors. That would be so equal to 4 1 2 3 4, which I have just marked, and the atom which is at the center of the face, front face, the face which I have let's say, let me write down the atoms as 5 and okay, with the different color, the 5 and 6. So this face 1 2 6 5, the atom which is present at the center of this face, which is this is also situated at the same distance, because we have to travel a by 2 distance here in this direction, and this a by 2 in this direction. So ultimately the distance between the O atom, which I marked with the O in the beginning, and this particular atom is nothing but a by root 2 again. Okay, so similarly we can find out others. If you go to the other side, let's say the atom which is at the center of this particular face, this atom, this is also at the same distance. Similarly, if you go to uh, you reach to this particular atom, this is also a by root 2 distance. If you reach to the this particular atom at the center of the floor, this is also a by root 2 distance. And if you go to the adjacent cube, for example, let's say if you find out the distance between the the atoms which are present, let's say, uh, what I'm saying is this, if if I want to find out the distance between this particular atom and the origin, the reference atom that we have chosen, this is also a by root 2. Okay, so all this, if we count in this fashion, uh, so this turns out to be that the number turns out to be 12. Okay, so mathematically also, let's say write down the if I consider this to be as my origin, and if I write to wish to write out the coordinate of any of the nearest neighbor which is situated at a by root 2 distance. So let me write down, suppose I this choose my this direction to be positive x-axis, this direction to be positive y-axis, and the z direction is perpendicular to both x and y following the right hand rule. Then the coordinate of this point 3, this atom 3, the coordinate will become a by 2 comma a by 2 comma 0. Okay, and if this is the coordinate of one nearest neighbor, so similarly we can find out other also. So there would be like a by 2 comma 0 comma a by 2, and let's 0 a by 2 comma a by 2, and minus a by 2 comma a by 2 comma 0, a by 2 minus a by 2 comma 0, minus a by 2 0 a by 2, 0 minus a by 2 a by 2, 0 a by 2 minus a by 2, 0 a by 2 comma 0 minus a by 2, and minus a by 2 minus a by 2 0, and minus a by 2 0 minus a by 2, and 0 minus a by 2 minus a by 2. That's it. So this makes it 3 4 6 9 and 12. Okay, so these are 12 total 12 nearest neighbors present in the FCC structure. Okay, similarly we can go to the second nearest neighbors. So if you wish to find out, let's say, the distance from the second nearest neighbor. Okay, so distance from the second nearest neighbor. So if we focus our attention back to the cubic unit cell, face centered cubic unit cell, so something of this kind. Okay, so the nearest neighbor we already found out. The second nearest neighbor that we see, for example, this was our reference atom, again the same reference atom. So the second nearest neighbor that we found out turns out to be this one, because this particular atom, the distance between these two atoms is a. All right, try to find out the distance from this darkened atom to the any other atom other than this p atom. We will see that the distance would come out to be greater than this the op distance, and that will not be qualified as second nearest neighbor. So okay, so this particular p atom is the second nearest neighbor atom, so the distance between op is this is a. So this distance from the second nearest neighbor. Second nearest neighbor. Okay, and if next question obviously arises that how many such second nearest neighbors exist. So number of second nearest neighbors. Number of second nearest neighbors we can find out by, again, mathematics if you wish. The coordinates of p would be 0 a 0. Then in that case it will be others would be the items which will be situated at the same distance a and having the coordinates like 0 0 a 0 0, and minus a 0 0 0 minus a 0 0 0 minus a. These will be the same these will be the atoms which will be situated at the same distance a from this atom O, origin O. So in that sense, the total number of second nearest neighbors is equal to 6. Okay, so let's go to the other thing, that is the third nearest neighbors. So if I want to find out the distance from the third nearest neighbor, so next thing we like to find out the distance neighbor. So if you wish to find out the distance from the third nearest neighbor, so if we go back to our reference atom O here, and we would like to find out the third nearest neighbor. The third nearest neighbor turns out to be this particular atom, which I have marked as let me mark with a different color also. So this particular atom. So if we find out the coordinate of this atom, let me mark with a Q. So OQ, if you find out the distance between OQ, then the coordinate of Q is, if I choose this to be my, let's say, x-axis, this is my y-axis, and the z-axis is perpendicular to the x and y both. Okay, so in that case, this coordinate turns out to be a by 2 a by 2. These are the coordinates of point Q. Okay, so we have to go a by 2 in the x direction, then a in the y direction, and then a by 2 in the z direction. So the distance OQ will turn out to be from the origin O. So this is my origin O. So this would turn out to be a square by 4 plus a square plus a square by 4. That is a square by 2 plus a square, that is root 3 by 2a. Alright, so that's what we get as the distance from the third nearest neighbor. And how many such nearest neighbors exist? So for that we'll have to do a little bit of permutation and combination, and that is number of third nearest neighbor. So the coordinates of point Q I've already written as a by 2 comma a by 2. Okay, so if we consider all the permutation and combination of this a by 2 a by 2 a by 2, so we will find out that the total numbers will turn out to be 24 indeed, and this will be as this: a by 2 a by 2 a by 2 a by 2 a minus a by 2 a by 2 a by 2 minus a by 2 a by 2, and then a by 2 minus a by 2, then a by 2 a by 2 minus a minus a minus a by 2 a by 2 minus a by 2 minus a, and then minus a by 2 minus a by 2 a by 2 minus a by 2, and the a minus 2 minus 2 minus a by 2 a minus a by 2 minus a by 2 minus a by 2 a minus a by 2 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 minus a minus by 2 a by 2 a by 2 minus a by 2 a by 2 a minus a by 2 minus a by 2 a by 2 minus a by 2 a by 2 a, and minus a by 2 a by 2. Okay, so that's how we get the 24. Let me check, we got the 24 now. 3, 3, 6, 9, 12, 15, 18, yeah, there are 24 in numbers. So the total number of third nearest neighbors in FCC is 24. Okay, and okay, so next thing we'd like to know is volume of the unit cell. One of the unit cell is simple, it is A cube. And what is the packing fraction? Packing fraction is also very simple to calculate. The effective number of atoms are 4. The volume of the one atom is, each atom is 43 by pi r cube. Volume of the unit cell is A cube. And we know the relation between R and A as well. So we have already found out that the relation between R and A was R equal to A by 2 root 2. So R was A by 2 root 2. So if we plug this relation here, so what we are going to get is 2. So ultimately we are going to get pi by 3 root 2, which is equivalent to 74%. So atomic fraction is 74% in FCC structure, which is a closed packed structure in 3D. Okay. It's a closed packed structure in 3D and in 3 dimension. So that's what we had to discuss for the FCC structure in the present video. Thank you so much. Thank you.